All right, so I started the recording, everybody. And if you go into the classroom under course content for week 5, there's a bunch of PowerPoints here. You'll notice that some of the PowerPoints, like when you click on PowerPoint Lecture 2, there's going to be a lot of blank slides in it, like with nothing written in them in the text area. That's because for this lecture here, we're going to be doing a lot of writing notes. And it's very easy to just say, oh, I'll zone out and not pay attention, or I'll wait for Matt to show me his his writing in the classroom. But I really highly encourage you to follow along with me. For some reason, this section tends to be I don't want to scare anybody, but for some reason, this section tends to be one of the hardest in the class, just because sometimes the concepts are a little weird, and people haven't done these type of problems before. So it just really helps if you write the notes as I take them. Okay, that's my suggestion. So and also if I end up going too fast or something during these slides, just let me know and I'll slow down. Okay. So what is going on in this section? So this section is about probability. Okay. And I really, really enjoy teaching this section, even though I said it's one of the harder ones. To me, it's one of the most fun. I don't know if I've told you guys this before, but did I ever tell you I used to live in Las Vegas? Did anyone ever heard me mention that before? Okay. Yes, so I have. So I got to practice probability quite a bit while I was living out there, and that's a joke, by the way, but a true joke. And so we'll work some casino game stuffs and game problems. We'll actually do one of our first examples would be a casino game, but it's the topic of probability, and I like to just note a few things. Okay. This topic, it starts off very easy. And I'm going to also say boring as well, just being honest. The reason it starts off deceptively easy and boring is because we spend a lot of time talking about die rolls and coin flips. Okay. And those aren't necessarily the most exciting example. So I like to preface this section by saying, if you're a little bored with probability, just give it some time, because the concepts of coin flips and die rolls help introduce the basic concepts and topics of probability, and then it gets really, really interesting. So by the end of the second lecture, it will be very interesting, I promise. Just some of the examples we go over in those sections they're just a ton of fun. So one of the first questions we'll work in class today, excuse me, is something like this. If you flip a coin 3 times in a row, so imagine you take a fair coin, okay, and you flip it and you record your results 3 times in a row. I want to find the probability that you get heads 3 times in a row. Okay. I'm just curious, does anybody know the answer to that? If you flip a coin 3 times in a row, what's the probability to get heads 3 times in a row? Does anybody have a guess? No guessing? Nobody wants to chat or turn on their mic for that one? No? Okay. So here's the thing. I in all my years of teaching, I've only, which is a long time because I've been doing this 12 years now, I've only had a student get it right once on the first try. Okay. So even something like flipping a coin 3 times in a row and we want to get heads, 3 times in a row, it's not 50. Nope. It's none of the chats have it right. It's actually a little bit, deceptively hard if you don't know how to tackle probability. Okay, so that's what I mean by, like, it starts out with just coin flip die rolls, but it's actually like a little bit challenging how you set this up. Okay, so I promise you before the first break we'll answer that question. It's not 25. Nope, nope. We'll stop taking guesses. Okay. So to start with, that's the right answer there. Yes, and we'll put it as a decimal, but I'll explain to how we get to there. So I want to start with some basic definitions of probability. Okay, and these definitions are going to come up throughout our lectures. Okay, so in probability, what we're going to do is we're going to perform what we call experiments. Okay, so this is our first definition. It's an experiment. Okay, we'll also refer to it as a probability experiment. Okay, so what a probability experiment is, it's an act or process that leads to a single outcome, okay, that cannot be predicted with certainty, and can be repeated. So an experiment here has 2 key components. It has uncertain results. When I say uncertain results, what I mean is I don't know for sure what's going to happen. Okay, like when I flip a coin. Okay, what are the 2 outcomes for flipping a coin? What are the 2 when you flip a coin? What are the 2 things you can get?
Head and tail.
Heads and tails, right? But before I flip the coin, do I know for sure what I'm going to get?
No.
No, you don't. Okay, so that's what I mean by uncertain results. And then the experiment is also repeatable. Okay, so uncertain results and repeatable. So let me give you an example of an experiment here. Flipping a coin. Okay. When I flip a coin, as I said, it's uncertain results. I don't know what I'm going to get, but can I repeat it? Can I just flip the coin again and again and again and again?
Yeah.
Yeah, for sure. So uncertain results and repeatable. Okay. Can somebody give me another example of an experiment? A probability experiment?
Rolling a die.
Rolling a die. Yeah. A die roll. So just so we're clear, when we talk about rolling a die in this course, it'll always be a standard 6-sided die. I know there's a bunch of other different sided die, but we're just going to always do it. Whenever you hear me a die roll, it'll be 6-sided. So again, uncertain results, no Dungeons and Dragons. That's correct. I'm a math teacher, so I did grow up playing Dungeons and Dragons. So I have all the different dice, but anyways, I digress. A die roll here, you got a little history of my life. There you go. As I was saying, so it's uncertain results, and it's total. And when I mean by uncertain results, like when I go to roll a die, right, I know I could get the numbers 1 through 6, but if I for sure knew what the die would come up when I roll it, I like to always say I'd still be living in Las Vegas. Okay. And then it's repeatable. I could just keep rolling the die, roll it over and over and over again. Okay, so these will be initially the first 2 types of problems we work, flipping a coin and rolling a die, because they're the easiest to visualize. Is everybody okay if I go on to the next slide?
Yeah.
Okay, so here's some other definitions. We have what's called a sample space. So sample space is a set. So in mathematics, a set is a list or a collection of objects. So the sample space is a set or a list of all possible outcomes of a probability experiment. And we denote it with the letter S. Okay. So what I want to do is I want to go through the 2 sample spaces for our 2 experiments, flipping a coin and rolling a die. Okay. So the sample space for coin flip. So I'm going to write a sample space with a funky looking S like this. And because it's a set, it gets set notation, which gets these special brackets. Okay. What are the two outcomes when you flip a coin? We've already said them in class.
Head and tail.
Yeah. So you can even write it as H and T. Okay. That's how I'm going to write it. Head and tail. Okay. So that's the list of all the possible outcomes for a coin flip. Okay. So let's do a sample space for a die roll. Okay, when you roll a 6-sided die, what are the possible numbers that could come up?
1, 2, 3, 4, 5, 6.
Yep, 1, 2, 3, 4, 5, and 6. Yep. So that's just the sample space. That's a list of all the possible outcomes for this probability experiment. Okay. So you can kind of see how some of these definitions are working. Okay, we're going to perform an experiment. Okay, and we're going to be able to know or figure out what the sample space is, all the possible outcomes. And then what we're going to be interested in is a specific event happening. Okay, so an event is any subset of the sample space. Okay, so we typically denote these events with letters. So you'll always see me in my definitions use E. Okay, E for an event. Okay, so like let me show you here. So let's let the event E, the first one, be, okay, flipping a head. Okay, so this event, all right, is a subset. Okay, so it also gets set notation. Okay, but the only way you can flip heads on a coin is you flip heads. You get an H. That's it. That's the subset. Let me show you another event with a coin flip. Okay, let's let the event E be that you roll an even number. So when you roll a 6-sided die, what are the ways you could roll an even number?
2, 4, 6.
Yep, so event E would be the subset 2, 4, 6. Okay. So we're going to have a sample space, which is all the possible outcomes, and we're going to be interested in just some specific event happening. Okay, the event E happening, like flipping heads or rolling an even number. All right, so here's some just, let me go back. Is it okay if I go forward? Mm-hmm. No problem. Okay. All right, so here are some rules of probability. Okay, first off, we're going to talk about how you denote probability. Okay. So the probability notation we're going to use in this class is it's going to be written like this. P is going to stand for probability, and then in parentheses, E. Okay, so this is going to be read as the probability of event E. Okay. So when you see something like this, it doesn't mean P times E. Okay. It means in our class in statistics, it's always the probability of what's inside the parentheses. Okay. So none of this has to be incredibly scientific how you write it. So if I were to say, denote the probability of doing the following things, I want to find the probability of flipping heads. I can write it a bunch of different ways. I could write it as the probability of flipping heads. I can also denote it as the probability that you get heads. Or when I'm a little bit lazy, sometimes you'll see me write it just like this. What's the probability you get an H? Okay. So what I'm hinting at here is nothing, what goes inside the parentheses here is just what helps you remember what you're trying to find the probability for. So all three of those things could mean the same thing. Okay. Does that kind of make a little sense in terms of notation?
Yeah.
I got one, yeah. So like probability of rolling even, you can write it a bunch of different ways. Okay, I want to find the probability you roll even, which is the probability you roll a 2 or a 4 or a 6, things like that. However you want to write it, just so you know what you're trying to find the probability of, okay? Probability of. And you'll see me as we do some of the harder problems, and this is going to be really important. So just like I'm going to throw really important like nuggets at you, and you just have to catch them and remember them. Okay. But how you write the problem, when you hear me say this, especially when we get to the harder questions, how you write the problem, it becomes really important. And what I mean by how you write it is what's inside the probability statement here. Okay. That becomes really important. All right, so can you have negative probabilities? No. So like, here's a problem. If you ever do a problem and you get an answer and it's less than 0, you know you did something wrong, okay? And can probabilities, can it be more than 100% chance? No, it can't. So if you ever do a problem and you get an answer that's greater than 100%, you know you did something wrong. So we in this class are not going to show probabilities as percentages, okay? They're always going to be shown as proportions. So what I mean by that, it's always going to be shown as decimals, okay? So the probabilities are always going to be between 0 and 1. Okay, so if something has a probability of 0, what do you think that means?
There's no chance of it happening.
Yep, no chance. Okay, all right. And if something has a probability of 1, what do you think that means?
100%.
Yep, always happens. Right? Like, what would you guys say the probability that I have a cup of coffee in the morning is? Is it a 0 or 1?
1.
2 if it was an option.
2 if it was an option. Yeah. Thank you. You know, I didn't know if my dry jokes were going over well today, but thanks for chiming in that one. That was a really fantastic joke. Thank you.
I gotcha.
You made my day. I appreciate that. All right. But to be in all seriousness, it was actually a trick question. The probability I have 1 cup of coffee is 0 because it's always more than 1. See what I did there? Okay, that was a bad joke. Sorry. All right, is everybody okay if I move on to the next slide?
Yeah.
Yeah. It is a trick question, Moshe, although I've been trying to cut back. I'm only on a half pot these days. All right, so here's just some of the rules written out in a little bit more official notation. Okay, so here's some additional ones. All right. So the probability of event E that we denote as PE, P of E that I said, it must be greater than or equal to 0 and less than or equal to 1. So any probability is always going to be bounded between 0 and 1. Okay. And this one seems a little weird. Okay. The sum of the probabilities of all outcomes, okay, for some probability experiment must be equal to 1. Okay. For any probability experiment. So I went off the slide there a little bit, but okay. So that is, and this is where it looks a little weird, and I'll try to explain it. Okay. If the sample space is equal to, and then what you see in parentheses there, it says E subscripted 1 is the first thing that could happen. E2 is the second thing that could happen, all the way to En. There's N things that could happen. What that means is if you take the probability of each individual event in the sample space and add them up, it has to sum to 1. Okay. Like for example, this is the sample space for a die roll. 1, 2, 3, 4, 5, and 6. There's 6 different things. If you take the probability you roll 1 on a 6-sided die, you add to it the probability you roll a 2. You add to it the probability you roll a 3, and so on. And you keep going. What do you think these all have to sum up to if I were to sum them up? Well, what does this say it has to sum up to?
1.
Yep. Yeah. If you take, so that's what I'm saying. If you have a sample space and you take the probability of each individual event and you add them all up, it has to sum to 1. Okay. That's a requirement for a probability experiment. Okay. This last one will become really handy when we start doing some of the harder problems in this class. So kind of keep this one in the back of your mind. All right. Is everybody okay if I go on to the next slide?
Yep.
All right, so we're going to compute probabilities using what's called the classical method for computing probabilities. You can compute probabilities with something called like the simulation method, but we're going to use what's called the classical method. So the probability, and it just goes like this. The probability of any event E occurring is given by and it's actually just like an incredibly simple formula, okay? So it's probability of E is equal to, and it'll be a very simple division problem, okay? It's the number of ways this event E can occur. So it's the number of ways E can occur divided by the total number of outcomes. Okay. So whenever we go to do a problem, initially, you know, especially these simple ones, especially these real simple ones, we're going to be like, okay, what's the classical definition or classical method for solving a probability? Okay, boom, it's a simple division problem. We have to figure out the number of ways E can happen, and then we have to figure out the total number of possible outcomes. But if you look back, I'm just going to go back a few slides and I'll come back to this. This is why we have some of these definitions. The sample space is the list of all possible outcomes. Well, if you count the number of items in a sample space, that's the total number of possible outcomes. And then if we're interested in a specific event, well, this is the number of ways that that event can happen. It's just the number of elements in E divided by the number of elements in the sample space. And that's it. So what ends up being hard with probability is at least for these classical definitions is like figuring out the total number of outcomes or figuring out the number of ways E can happen. It's not like the division is the hard part. That's the easiest one. All right, so let me ask you a question here. Okay, and you'll all know the answer to this, and then I'm going to show you the notation for this on the next slide. If you flip a fair coin, what's the probability that you get heads on the coin?
1/2.
Okay, so it's probability of heads. So I'm actually going to do it on this slide. We're going to actually do a die roll on the next one here. Yeah. So look, just using the classical definition here. It's the number of ways to flip heads. And we're going to divide it by the total number of outcomes. Total number of ways to flip a coin. All right, so if you're going to flip a coin, how many different ways can it come up as a head? Is there only one way you can flip a coin and have it be heads?
Yeah.
Yeah, and how many total outcomes are there for a coin flip?
2.
There you go. Boom. That's how you got that 1/2. And look, going back here, flip heads, there's one element in this sample space. Total number of outcomes, there's 2 elements in this sample space, 1 divided by 2. That's it. That's how we did that problem. All right, whenever we do these problems in our class, you can leave it as a fraction. That's fine. Yep, we're going to do an example with dice next. Yep. Or when you divide it, you can leave it like that. Also, I am fine in this class if you do a problem and you get a fraction and you don't even reduce it. That's totally okay with me in this class. Okay. All right. Is everyone ready for me to see? Jamie asked in the chat there to do a dice one. I got a dice one lined up next. Is everybody okay if I go to the next slide?
Yeah.
Okay. All right. So this is a sample space for a die roll. Okay. We said there were 6 outcomes for a die. All right. So 1, 2, 3, 4, 5, 6. Okay. And again, here is the classical definition. Okay. So the question is this right here. What is the probability you roll an even number? Okay. An even number. So look, I'm just going to go back real quick in the slides. Rolling an even number. Look down here where my mouse is. We said there were 3 ways, 2, 4, and 6. Okay. So the probability you roll even, and I'm just going to even write it here. Okay. It's the number of ways to roll even. Divided by the total number of possible outcomes. And in this class, sometimes when you see me do this pound sign, that's going to be what I'm going to write for number. Okay. So whenever you see that, whenever you see it, just be like, Matt, whether is that symbol? That's my total. That's my symbol for number. So look, the number of ways you can roll an even number is 2, 4, and 6. Total number of ways you can roll a die, 1, 2, 3, 4, 5, 6 ways. So in this class, I am totally fine if you solve a problem and leave it as 3/6. That's okay with me. If you want, you can reduce it. You can reduce this to 1/2, or you can write it as a decimal. That's totally fine with me. Okay. So let me ask you this. Does it kind of seem straightforward so far? Is it not too bad?
For now, yes.
For now, yeah. Right? Like, I mean, come on. Flipping a coin and rolling a die, pretty easy, right? But so obviously, this isn't the type of problems we're going to do. Okay, so we're going to make them a little bit harder. Okay, and I'm going to show you all the tricks. Okay, to be able to answer these problems. All right, I'm not going to hang you out to dry, as they say. All right. Sorry, my mic just fell over. All right, are you guys ready?
I got it. Mic drop.
Mic drop. Yes. You got jokes today. That's good. All right. You guys ready to do the first harder example?
Yeah.
Yeah. A little bit of trepidation in your voice there. Okay. All right. So there's a little bit of a typo in the slides here. This says rolling a die 3 times in a row. What it's supposed to be here, the first example we're going to do, sorry for that typo, okay, is flipping a coin 3 times in a row. Okay. So let me set up the problem. Okay, this is, suppose you flip a fair coin 3 times in a row. Does anybody know what I mean when I say a fair coin?
Order?
So what a fair coin means, forgive me for not making this clear, is that it has the exact same probability that you will flip heads or tails. Okay, what it means is the coin isn't weighted heavily on one side. So you might hear the terminology of fair coin, in the future. but sometimes if I just say flip a coin, it'll also be the same meaning as a fair coin. It just means you have equal probability of getting heads or tails. That's all it means. Okay, so suppose you flip a fair coin 3 times in a row and record your result. Okay. So let me show you how I'm going to show the outcomes. Okay. Can I flip a coin 3 times in a row and get 3 heads in a row?
Yeah.
Yeah, that could happen, right? I'm going to show that outcome as HHH, 3 heads in a row, HHH. Okay. I don't know. What's another outcome that you could get?
3 tails.
Absolutely. You can get 3 tails in a row. All right. Someone give me one more. What's another outcome you could get?
2 heads and a tail.
But now here's the thing. There's a bunch of different ways you could do that. This is where it gets complicated. So 2 heads and a tail. Could you go tail, heads, heads? Is that one way you could do it?
Yeah.
What's another way you could do it? Yeah. You could go head, tail, head, and so on. Like there's a bunch of different ways you could get 2 heads. So you have to be very careful there. All right. So here are the questions I'm going to ask. First question. Is this a probability experiment?
Are you referring to the actual coin?
Well, no. So what I'm
Yes, it is.
Okay, so yeah, let me just answer the first question. So when I say is this a probability experiment, I mean the whole thing. Okay, flipping a coin 3 times in a row. And
Well, yeah.
okay, someone said yes, it is. But why? Why is it a probability experiment? What 2 requirements?
One, you said
Chance.
it can be repeated.
Can be repeated, absolutely. And
it's off by chance, no?
and what do we say? And someone has it right there. Jamie has it. Uncertain results. Yes.
Yes.
Yes. So yes, this is a probability experiment because it is repeatable with uncertain results. Okay. So now the next question here, okay. For these simple problems that involve like flipping dice and rolling coins, sometimes it's really important to figure out what the sample space is. So let's list or find the sample space. For this experiment. Okay, so now even before we begin, okay, sometimes it helps before you start to figure out the sample space by asking yourself, how many total different outcomes do you think there are for this experiment? A little bit more than 2. Right, so Jamie, like look here, like here are just 4 different outcomes. This is what I mean, right? So there's going to be more than just these 4. Okay, so there's 2 outcomes for just a single coin flip, but now we're flipping 3 times in a row. Yeah, yep, all good. So no, for this entire experiment, it's not 27. Why'd you guess 27, Melissa? I'm curious.
I thought maybe because you got 3 choices when you're flipping it 3 times, maybe 3 to the third. I'm not sure.
You're so close. You're close. You made a little bit of a mistake. Julia, that is the right answer. Okay, there's 8 outcomes to this experiment. Can you explain to us how you got that if you want to, or, you know?
We did this briefly at the end of MATH140, and I think it's because you start off listing like the 4 I don't know. I think I multiplied by 2, but I'm
That's
not
it.
really sure.
So
I multiplied by 2.
So here's and this is a tip for everybody. Okay, in this class, when you want to count the number of ways things could happen, there tends to be a multiplying effect. Okay, so when you flip the coin the first time, okay, so here's the first flip. All right, how many outcomes are there for the first flip? Two things could happen, right? You could flip heads or tail. Now for the second coin flip, how many things could happen? Is it also two? Yeah. Oh, hold on. Sorry about that. And for the third flip, how many things could happen?
2.
Yeah, because there's only heads or tails. Yep. So there, and listen to what I said. There tends to be a multiplying effect when you're counting. So 2 times 2 times 2. All right, that tells me there should be 8 total outcomes to this experiment. Now, what it is now, it's our job. Our job is to find all the possible outcomes. Okay, so first off, we know there should be 8 outcomes. Okay. So I'm going to show you a trick. Okay. And this works really well for finding the sample space when there is a small number of outcomes. So you can use this method. When there is a small number of outcomes. Okay. Yeah, go on ahead, Jamie. You have a question.
Are we only using the number 3 because it's asking how many, like, to flip a coin 3 times in a row?
Yes, that's why, like, you see how I have like 3 things.
Yeah, so that's why.
Yeah.
Okay, thank you.
Mm-hmm. Okay, so there should be 8 outcomes. Okay, so the method for finding the sample space from an experiment with a small number of outcomes, you can use what's called a tree diagram. Okay. And what a tree diagram does is you think about it as a tree, and each branch, you're going to see the tree as I build it. Each branch of the tree is going to represent a different outcome. So you start your tree diagram with a dot. I know it seems silly. Start it with a dot. And you do a header here and you write the first flip. Okay, so when you flip a coin the first time, what are the outcomes you could get? Don't overthink this. When you flip a coin, what are the things you could get?
Head or tail.
You can get a head or a tail. So what's going on here is my branches are starting to show the possible outcomes. I can get a head or I can get a tail. So that's just the first flip. Okay, now I'm going to go to my second flip. Okay. When I flip the coin a second time, what are the outcomes I could get?
2 heads.
Well, hold on. No. I'm just, when you can get heads or tails again, right? Do you see what I mean? Like you can get heads or tails again. So maybe you flipped heads. So on your second flip, well, I could also get heads or tails. But maybe you flipped tails the first time. So then on your second flip, you could get another heads or tails. Now we're going to go to our third flip. Okay. Now, when you flip a coin again, the last time, what are the possible 2 outcomes you could get when you flip a coin?
Head or tails.
Again, I
Tails.
head
So
and a
maybe,
tail.
so watch my pen here. So maybe you
Tail.
flipped, yep. So maybe you flipped heads, then a head. So then on your third flip, you can get heads or tails. But maybe you flipped heads, tails, and then on your third flip, you could get again heads or tails. And then you're going to keep going off every branch. Gets a little tight here. Sorry about that. And what you have here is you have a tree that has 1, 2, 3, 4, 5, 6, 7, 8 total branches. Okay. And this tree that's fallen on its side, what you can do is you can look through this tree and you can get the entire sample space. All right. So watch as I traverse the tree, what the sample space is going to be. So the first outcome could be head, head, head. Do you see how I followed that branch? Head, head, head. Then the next branch goes like this. Watch my pen. Head, head, tail. Everybody see how I did that?
Yes.
Now watch this pen. So I've covered this entire branch up here. So now I'm going to go head, tail, head. And then the last branch that starts with a head goes head, tail, tail. So I've covered the first 4 branches. So now I've got to go to this branch down here. It goes tail, head, head. Tail, head, tail. And then tail, tail, head. And then tail, tail, tail. And look how many things are in there. 1, 2, 3, 4, 5, 6, 7. There's the 8 things I said there should be. What do you think?
I am following.
Sorry.
Is it? You can be honest. A little confusing the first time you see it.
Yeah.
Yep, I totally get it. And yep, tedious is the exact word I would use for this. So I'm just gonna be honest with you, okay, with everybody. These type of problems that I'm doing right now, super. You know what? I don't even care that we're recording. They're kind of boring and they're a little too simplistic for what we're driving towards. But they just help us. Yeah, we would never do this for something like 10 flips. Okay. We do this for the very small problems like flipping a coin 3 times, just so you can kind of start to see the process of finding sample space and probability. But then once we get to harder problems, we don't do this type of stuff. Okay. So just relax, don't stress too much about it. Okay. Is everybody okay if I go on? And now that we've got, yep, I'm gonna load the calculator up in a second. Yep, we're gonna use it a bunch actually. Okay, is everybody okay if I go on to a question now about probabilities from this? Okay. So the third question here is was what I started with. If you flip a coin 3 times in a row, okay, what's the probability of getting 3 heads? Okay. So it's the probability that you flip 3 heads. Okay, so to answer this probability question, and I'm going to come back to this slide in a second. Okay, so don't stress if you haven't finished copying. But to answer these very simple probability questions, we're just going to use this classical method. Okay, this classical definition. Okay, so it's a simple division problem. Yep, that's it. It's the number of ways to flip 3 heads divided by the total number of possible outcomes. All right. So Melissa beat us to it, but let's start with the denominator here. How many total outcomes did we say there were for flipping a coin 3 times in a row?
8.
Yep. If you look back here, there are 1, 2, 3, 4, 5, 6, 8 things in the sample space. So now all you have to do is look back in here, all right? And you say, well, how many ways out of the 8 is exactly 3 heads? Well, if you look here, the only way you can get 3 heads is getting HHH. So it's 1 out of 8, which you can leave just like that. Or you can grab your trusty calculator if you want and do 1 divided by 8. And you get that 0.125. So now does it kind of make sense? All the definitions that I started class with, I know it took us 48 minutes to get here, but not too bad. Doesn't seem too bad.
I'm following the procedures, but my question with the final number is that a percentage, or we're just leaving it as a decimal?
It's always a decimal. So probabilities are never reported as a percentage. Okay.
Okay.
Oh, I mean, over time, people say it like, oh, it's 12.5%. Okay. But when we report answers, it's always going to be as a decimal like that. All right.
The answers will always be between 0 and 1.
Always be between 0 and 1. Yep. And like when you go to do your next exam, I'll ask for an answer. And like, if you were to write it as 12.5%, the system will say you got it wrong. So you have to put it as a decimal. Okay. Let me do one more. Okay. So if you flip a coin, three times in a row, what's the probability of getting 2 tails? So it's the probability to flip 2 tails. All right, so I'm going to skip the classical definition here, okay? And just jump right into the fraction part. All right, what's the denominator here? How many total outcomes are there to this experiment?
8.
I'm going to talk about that, Melissa. Okay, there's 8. So this is incredibly important, especially when we get to the harder problems. You have to pay close attention to what it's asking. How many tails do I want you to get?
2.
I want you to get 2 tails. Okay, so we have to count the number of ways that could happen. Okay. No. Is this 2 tails right here? HTT?
Yes.
Okay. Nope. Is THT 2 tails?
Yes.
Okay. Is TTH 2 tails?
Yes.
Yeah. So now you have to be careful. How many tails is this one?
3.
Is that 2 tails?
No.
That's 3 tails. So you have to be very, very careful to the wording of the problem. So how many ways can you get 2 tails? Yeah. It's 1, 2, 3 ways. Yeah. So this is 3 out of 8, which gets you 0.375. All right, what do you think? Not too bad? Terrible. I wish I signed up for college algebra. That's what everyone's thinking right now. I hope not. Okay. All right. I think this is a good spot for a break. I know we had a lot of terminology. Calc 2 is a tough class. Calc 2 is a real tough class. Yeah. Yeah.
Okay, so you teach calculus too, or pre-calculus?
What do I teach? I mostly just teach statistics. I think I'm teaching Calc 1 next fall online.
Okay, thank you.
Yeah, no problem. You don't want me for calculus anyways. I tell too many jokes. You want a hard teacher for that one. Okay.
I would want you to for every subject.
Oh, don't butter me up. Okay. All right. Let's take an 8-minute break here. Okay, or 7.5 minutes. We'll start back up at 2:00, and then all we're going to do with the time we have left is just a couple more examples. Okay. Is that okay with everybody?
You're the boss.
I am the boss. All right. I'll be back in. I just want to grab a drink of water. I'll be back in 7 minutes. All right, everybody. Let's finish up for the morning. So what I want to do is I want to do at least 3 more examples of this stuff. Some of them will go pretty quickly. And then maybe if we have time at the end, I'll start some of the more complex formulas or theorems in probability. All right, everybody ready to jump on and finish for the afternoon? Ready? Boom. Okay. So the next example I want to do is I want to do a casino game. Okay. I just want to preface this by saying I'm doing this just because I think it's interesting and it's in a way you can see probability. But I would never ask you a casino game question on an exam. Okay. So don't stress too much about, if you know the rules or anything. But the game I want to talk about is the game of craps. Okay. How many people in here have ever seen the game of craps? Okay, I don't want to ask if you played the game, but how many people know of the game of craps at a casino? So it's okay if you haven't. How many people have no idea what the game of craps is? Maybe that's a better question. Nope. Okay. So I just want to explain it just a little bit, not like the intricate rules, but just like the basics of it. Okay. Because this casino game is, it's just a probability question. And I always like to, does anyone know what movie this is from, where casino is? Anybody know? Got Robert Downey Jr. From the movie Iron Man, actually, the first Iron Man movie. They go drag him out of a casino. But anyways, so this is the game of craps, okay? You have this table, okay? And people sit around the table. Okay? This is a really terrible drawing, but hopefully everyone has smiles because they're winning. Okay. And what one person does, okay, this person here, okay, this person is called the shooter. Okay. A person rolls 2 die. So this person takes 2 die and they roll 2 dice. So 1 die comes up with a 1, let's say, and 1 die comes up with a 2. So the person rolls 2 dice and sums the result. Okay. So like this person here who rolled a 1 and then they rolled a 2. What would we say the result is in the game of craps? Yep, that's it. The person rolled a 3. Okay. I always like to tell this story just to lighten it up a little bit. First time I took my girlfriend, who's now my wife, to a casino, we went to Atlantic City. And again, I'm not saying any of you should ever go to a casino. That's not what I'm saying. Okay. But I was like, oh, hey, honey, let's go play some craps. It'll be fun. So, we went and played like $5 at the $5 table. But she took her dice. The first time she took her dice and she threw them to the other side. Does anybody have a guess what happened when she threw her dice to the other side? She had never done this before. Worse than that, my poor wife took the dice and she threw them so hard she hit this person right here. She goes, whoosh, whoosh, and she hit that person. Oh, it was really funny. Yeah, it's actually really common at the casino. Everybody just kind of laughs it off. And they just take the dice and they give you new ones because everyone's like, oh my gosh, it's a newbie here. So it's funny. I don't even remember. I don't think you should ever consider going to a casino to make money. But So I got a couple questions for you here. Okay, so don't worry about the rules of craps. There's a ton of different rules for the game of craps. I don't want to get into them, but what we're going to do here is the following. Okay, is you're going to roll 2 dice and you're going to sum the results. Okay, so roll 2 dice and sum the results. So the first question is this a probability experiment? Does this have uncertain results and is repeatable?
Yes.
Yep. Yes. Has uncertain results and repeatable. Okay, that's the important thing. All right, so now this is a little weird. Okay. The next thing on the next slide, I'm going to show you what the sample space is. We're actually not even going to write it out. But the question is how many outcomes are there? All right, and what I mean is how many possible die roll combinations are possible. So how many different die roll combos are possible? Okay. Well, remember when I said you want to count things? I said there tended to be a what type of effect? It started with M. Tended to be a multiplying effect. Okay. So when you throw the first die, okay, when you roll this first die right here, okay, how many possible outcomes are there for the first die? Yep, yep. And then when you roll the second die here, how many possible combinations, how many possible outcomes are there? Okay. All right. So now remember, there tends to be a multiplying effect. Okay. So if there's 6 outcomes for the first die and 6 outcomes for the second die, okay, how many total outcomes, how many total possible different die combinations are possible? That would be adding them, Jamie. But if there you go, 36, right? Because you want to multiply. So what I'm claiming here is there's 36 unique die roll combinations for the game of craps. Okay. So what's confusing about it is you're going to roll your die, and then once you get that unique combination, then you're going to sum it. Okay. So like this person here got a 1, then a 2. And that was one unique combination. And then because you want to count the total number of outcomes. And whenever you want to count the total number of outcomes, there tends to be a multiplying effect, Jamie, always. Yep. So let me show you now. So there should be 36. So let me show you what the 36 possible outcomes are. Okay. So when you look here, these are all the possible outcomes. Okay. And what's unfortunate is when you play the game, for this class, there tends to be a multiplying effect. So I don't want to say that the only way you count stuff is with multiplying, for a different class. But, for our purposes and the type of problems that we're going to do, there tends to be a multiplying effect when you start counting the number of different ways things could happen, the number of combinations things could happen, number of permutations. That's why I sometimes, when I say tends to, because I don't want to just be like, oh, this is the only way. And then, you have a different class down the line that talks about it differently. Okay. So if you were to play the game of craps, I'm not saying you should go to the casino and play it. I'm not. Okay. But they always have the same colored die. But if you could have 2 different die colors, it would make this a lot easier to understand. Okay. So I'm going to show dice results. I'm going to show results as ordered pairs. Okay. And what I'm going to show the ordered pairs are the following. Die 1 result, comma, die 2 result. So here is one combination. Okay. So what's going to happen here, the first die here is the first die, and this is the second die. So this, when you roll a 1, 1, this is the outcome 1, comma 1. Okay. But in craps, remember, in craps, we're not going to say you rolled a 1, 1. Okay. We're going to sum them. And we'll say you rolled a 2. Yep. Look here. This is why I wanted to illustrate this. This is the outcome. You rolled a 1 on the first die and a 2 on the second die. Okay. In craps, what would you have rolled? What would they say? Yep. You sum them. You would have rolled a 3 because 1 plus 2 is 3. But over here, look here. Here, this is you roll a 2 on the first die and then a 1 on the second die. In craps, what did you say you would have rolled though? Still 3. Yeah. This is my point. Okay. Rolling a 1 on the first die and a 2 on the second die is different. Is different results than rolling a 2, comma 1. They're different. Okay. You still say you rolled a 3, but you got there differently. Okay. So this happens for all the numbers that are not the same numbers. Like if you look here, this is a 1, 3. A different unique result is a 3, 1. The only thing that's the same, okay, rolling a 1, 1 is the same outcome as a 1, 1, a 2, 2, a 3, 3, a 4, 4, a 5, 5, and a 6, 6. There's only one way to do that. So you don't have to flip them like 1, 3, 3, 1. Okay. And you can see like it's like this for all of them. Here is a 2, comma 4 is different than a 4, comma 2 over here. Okay. And that's how you got this 36. There were 6 options here and 6 options here. Result. Sorry, it looks like an H. Sorry. LT. Sorry. Sorry about that, Alexandra. I've shown you guys what I write on, right? You guys see how small it is. It's not the easiest thing. Here, I'll show you on my camera here so you can see. I write on this little tiny thing. So sometimes my words get a little messed up. Like it's not even as big as my face. So sorry about that. All right. Everybody ready to see may I ask you some probabilities from this now? Okay. In the game of craps, what's the probability your result sums to 7? Okay. So again, this is the probability you roll 2 dice and they sum to 7. So to answer this, we're going to just do the classical definition. Okay. And what goes in the numerator is the number of ways to sum to 7 divided by the total number of possible outcomes. Well, how many total possible outcomes did we say there were for this game? Yep. So the denominator is 36. All right. Can somebody now let's start looking back here. Okay. Think about the ordered pairs. Okay. The first value is the first die and the second value is the second die. What are some ways you could roll 2 dice and have them sum to 7? What are some of the outcomes that you could get this? You get a 6-1, sure. What's some other ways?
3 and 4.
5-2.
4-3.
3 and 4, yep, and which is different than 4 and 3, yep. 2 and 5, and what's the last one? And 1 and 6, yeah. There's no other ways you could do it, right? So the probability that you would win, okay, would be 6 out of 36. Or win, I didn't mean to say win. That's a that's a game. That's a rule. Would be just 6 out of 36 or 1 out of 6. Or if you were to grab your calculator, it would be 0.166666 here. Which I'll round to 167. So do you see how once for these coin flip problems, like once you figure out the sample space, like the rest of it kind of just like, oh, all right, it kind of makes sense. So once you got the sample space, did this problem not seem the worst? I hear crickets, nothing. Sample space is the total number of outcomes, yeah. All right, let me ask you another one, okay? All right. Yep, getting the sample space, it's tricky. It's never, that can be hard for these simple problems, yeah.
I have a question, Professor.
Yeah.
Like if you asked us another number, like for p sum to like as an example, p sum of 8 or something, or p sum of,
Let's do 8.
we would have to like guess the numbers, right? Or...
No, let's do that. That's that problem. Yes, probability that you roll 2 dice and they sum to 8. Okay. So here's the thing. What's the denominator? What's the total number of outcomes for this? Anybody can help me. The 36 comes from the sample space here, because there's 6 ways for the first die and 6 ways for the second die. And you can see here, there's 6 columns of 6. So there's 36 for this.
Professor, if we should have a third column, would that be 6 times 36?
If you were to roll 3 dice and
Right.
sum their results, yes, then there would be 6 times 36 total number of outcomes. Yeah.
Thank you.
Yeah. All right. So let's do this problem where it sums to 8. Okay. Well, hold on. That's probably right, but let's just go through it. How many total number of outcomes are there for this experiment again?
36.
36.
Yep. Now let's go through and talk about the ways you can sum to 8. What are those outcomes? Can you, a 6 and a 2, a 2 and a 6. What are some other ones?
4 and 4.
5 and 3, 3 and 5. And then what did you just say? I'm sorry.
4 and 4.
And that's it. Yep. 7 and a 1 you can't get because on a 6-sided die, you can't roll a 7, right? So you just have to, yep. So here's the thing. 6-2 is different from 2-6, but 4-4 is the same as 4-4. So you can't flip that one. So it's exactly 5 out of 36. Yep. Which would be 0.139. And just we're going to do another example later on that talks more about how casinos make money. But have you ever heard the saying, the house always wins? Has anyone ever heard that saying? For
Yeah.
casinos?
Yes.
So this is how casinos make money. Okay, just this, as we're learning, probably like a practical application of it, right? So a casino might offer this as a bet, right? And they say the person will win 1 out of 6 times. But what they'll do is they'll say, they'll do something like this. Oh, for every $1 bet, if you win, I'll give you 3. Okay, so they're paying you 3-to-1 odds when the real odds are 1 to 6. So that's how casinos make money. Like, yeah, maybe you win in the short term, but if we were to do this experiment over and over and over again, eventually I'd take all your money because I'm not giving you even odds for it. So that's why I always like to caveat these and say, I'm not saying go to a casino, but at least you know what's kind of going on with them. All right, how about we'll end class with 2 more examples. That sound okay? We'll do one
Sure.
easy, we'll do one very simple one, and then we'll do one much harder one. Okay, so everybody okay if I move on, I mean? Okay. All right, so suppose you have this fun-sized bag of M&Ms, okay? And it contains 9 brown candies, 6 yellow candies, 7 red candies, 4 orange candies, 2 blue candies, and 2 green candies, okay? So you've got this fun-sized bag, okay? And they have these bags of M&Ms in it, and they're just like, only one color M&M in each bag, okay? So you're going to go into the bag and you're going to select one candy at random. Okay, so you're going to like shuffle them up and select one candy at random. So here's the first question. Okay, what's the probability you reach in and you get a yellow candy? All right. So this seems a little bit weirder than the previous problem. Okay. All right, well, what's the first thing you should do? Okay. You should figure out how many possible bags of candy there are, right? Does that seem reasonable? So does anybody have a guess at how many total bags of candy there are? I don't think it's 21, Julia. So the first thing
Is
you
it
have to-
1?
Well, hold on. So what you're doing here is you're reaching in and you're grabbing a bag of candy, right? So you got to figure out how many total bags are in the fun size. Okay, how many candies?
Professor, total candies or total bags? Because it seems it's just one big bag.
Total candies. I'm sorry.
All right, thank you.
My bad. There we go. Yeah, looks like there's 30 total candies, right? 9 plus 6 is 15, 22, 26, 28. Looks like there's 30. So if you want to find the probability of getting yellow, okay, you have to say, well, there's 30 total candies in there, okay? And how many of them are yellow? 6. So the probability you would reach in and get a yellow candy would just be 6 out of 30, right? And what would that simplify to? Okay. Yeah, you could take it like, you could do it this way, right? You could go 6 divided by 30 will get you that 0.2. It also simplifies to 1/5 as a fraction, like that. So now another one here. What's the probability you reach in and you get a blue candy? Well, how many total candies are in there?
2.
There's 30. Yep. And there's how many blue? Yeah. So
2. 2.
Yeah. So it looks like here this would be 2 out of 30, which simplifies to 1 out of 15 here. Okay. So look, I'm going to comment on the likelihood of each of these, of yellow versus blue, but let me show you in a little bit more detail here, right? So it's the number of yellow divided by the total number of sample space. Got you that 6 out of 30. Here's the number of blues, which was 2 out of 30. And if you look at it here, all right, what this means as when I talk about the likelihood, if you look to go from 2 to 6 is 3 times. So it looks like yellow is 3 times as likely than selecting blue. So for these simple problems here, like drawing candies from a bag, or later on in class, I'll actually do marbles from a bag. The first thing you're going to have to always figure out is the total number in each. And then for any specific one I ask you, just divide that number by the total. That's it. All right. I'm going to open up, if you go into the lecture slides now, there's this lecture called Probability Lecture number 2. Okay, if you don't have that, download it and or at least start taking notes, because we're going to continue this class, and next class is just going to use this entire PowerPoint. Okay. Sorry if I seem off a little bit. My son just woke up from his nap, and it's my wife is getting him, so it's kind of just throwing me off a little bit. So my apologies. All right. Everybody, thanks. Yeah, he had a rough day. He got up at 4:30 this morning. So he is not like us today. I mean, in party animal, he went to bed at 7 last night. So, all right. So what I want to do in this lecture here is I want to start talking about the advanced rules of probability. So we're just going to start by recalling the definition of probability. And this is just the classical definition. Okay, we're always going to use this initially for our problems. So it's the probability of any event is equal to, just very simple. Again, it's the number of ways the event can occur, and it's always divided by the total number of outcomes. Now, this next problem I'm going to have here, okay, this problem is like, it encompasses everything I've talked about for the last hour of class. So if we can all do this together, or if you have an understanding of how to do this, then you've really, really mastered the concepts from the first part of class. All right. Everybody okay if I go on? Okay. So on your next exam, which I think is the 16th according to the syllabus, it'll cover probability, and I always ask a coin flip die roll type of problem. So something like this, okay? So here's the problem. Suppose you flip a coin and then roll a die, okay? And you're going to record your results, right? So you're going to flip a coin in the air, you're going to catch it, you're going to look at your result, and then you're going to roll a die, and you're going to look at that result, okay? So this is how I'm going to show the results, okay? Flip a coin and then roll a die. Could I flip heads and then roll a 6? Is that one thing that I could do? Yeah, sure. What's another thing that you could do? You get a tail and a 4. Sure. What's one last thing you could do? And you get an head and a 1. Okay, great. So here's the first question, all right? Is this a probability experiment? Yes or no, and why? What do you think?
Yes.
Yeah, okay. And what 2 requirements do probability experiments always meet?
It should be uncertain. The results should be uncertain, and it should be repeatable.
Yep, the results are uncertain and repeatable. And look, this is absolutely true. When I flip a coin and then roll a die, I don't know what I'm going to get for sure. Okay, so that's the uncertain part. And then it's totally repeatable. I could just keep doing this over and over and over again. All right, so the next question says, what is the sample space? So what we have to figure out is all the possible outcomes to this experiment. Now, listen, even before we begin, okay, how many total outcomes do you think there are for this experiment?
I will guess 8 and 36.
Okay, hold on. So there's only one die here, okay? So don't confuse this with the previous one where you flip a coin 3 times. So I'm only flipping the coin 1 time, and then I'm only rolling the die 1 time. Does anybody have a different guess?
1, 6.
No. Why'd you get 12? That's the right answer. If you want to share. Yeah. When you flip a coin, how many total outcomes are there? 2. When you roll a single die, how many total outcomes are there? 6. So 2 times 6 should give me 12. Okay. So to do this, you can use a tree diagram, but I actually think there's a little bit easier way to do this. So the way I'm going to write the sample space is like this. Okay, and then you'll immediately see the pattern. If I flip heads and then I roll a 1, that's one outcome. What's another outcome where I flip heads? I could flip heads and then roll a, what's another thing you could do? Yep, and then H4, and then H5, and then what's the last one with the heads? Yep, thank you. Now, these are all the possible outcomes when I started with heads. But what else could you do when you flip a coin? Yep, you get T1. You can get a T, then a 2, T, then a 3, T, then a 4, T, then a 5, and then T, then a 6. And look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 possible outcomes here. Okay. All right, so I'm going to ask you 2 questions here, and these questions are going to be the introduction to, excuse me, some of the harder problems we're going to do in this class. And actually on Thursday when we come together, I'm going to come back and show you some advanced formulas and then rework these problems with the formulas so that we know that the formulas work. All right, but so here's the first, I have 2 probability questions. First one says, okay, you're going to flip that coin and then roll a die. What is the probability that you flip heads or, now this is important, or roll 6? Okay, what's a little bit different about this problem compared to any of the other problems? That's the right answer, Melissa. Yeah, but I'll get there. What's the word in here that's a little confusing or a little different? Yeah, the or. Okay. So whenever we're going to be working later on in class, a lot of these problems are like, hey, well, what's the probability that this or this happens? Okay. And so the or you're going to see later on is going to imply a certain type of mathematical operator. But for now, let's just answer this question using the old school method. Okay. So what goes in the denominator is the total number of outcomes. And what goes in the numerator is the number of ways to flip heads or roll a 6. Well, how many total outcomes are there for this experiment? Yeah. All right, so then what we have to do is we have to look through this sample space here. Okay. And we have to figure out the number of ways you can flip heads or roll a 6. So look at this outcome here, H1. Is that a head or a 6? Yeah. Like logically, when you see the or statement, all you need is one of the two requirements to be met. Yeah, that's a head or a 6. How about H2? Is that a head or a 6? Yep. And then H3 is a head or a 6. 4, H5, H6. Those are all heads or 6s. Is T6, does that contain a head or a, yep. Yeah. Yeah. So it looks like there's 1, 2, 3, 4, 5, 6, 7. 7 possible ways this could happen. So this answer would be 7 out of 12. Which gets me 0.583 when I round it. All right, now notice the subtle difference here. Okay, the next question is, what is the probability of flipping heads and getting a 6? Yep. So again, I'm just going to write it with the classical definition. Okay. It's the number of ways to flip heads and roll 6 divided by the total number of outcomes. Well, again, there were 12 outcomes. And logically, what's the key word in here that's a little different? And you guys all have the right answer there in the chat, but what's the key? Yep, the and statement. Okay, because I wanted to find the probability of this and this happening. So logically, for an and statement to be true, you need to have both a heads and a 6. Yep, you need both. And that's just this outcome H6. Okay. So that's just the 1 here. All right. So here's, I'm going to do one last definition. Actually, I thought I want to go just a couple more minutes. We'll do one more definition. But this is where we're kind of going in this class, where we're going to be doing these a little bit harder problems where it's like, okay, what's the probability of this or this happening? What's the probability of this and this happening? And you'll see next class that, I'm going to ask you a probability like this. What's the probability that you roll 4 6-sided dice and they all come up as a 1? Michael, this first one here, or the or the and statement? Do you want me to go over?
The or.
Yeah. So the or, for logically, like what this is saying is what outcomes have either a head or a 6. So like if you look at H1, that has a head, so it meets the head or a 6. Same with H2, H3, H4. H5 is a head or a 6. H6 is both, so that works out. So that's 1, 2, 3, 4, 5, 6 possible outcomes. But the way I got 7 is if you look at T6, T6 is also a tail. Is this a head or a 6? Notice how it has a 6. So it meets that requirement. So it would count because T6 contains a head or a 6. And what I'm going to show you guys in this class, yeah, no problem, is instead of doing these problems like this, I'm going to show you some formulas to eventually answer all this stuff. So you don't have to stress so much about the sample space. Okay, with the time we have left, just real quick, I just want to go over, is everybody okay if I go on real quick? Okay. I just want to go over one rule. So if you look in the Excel sheet here, you'll notice that I have like all these different rules. Like here's rule 2, rule 3. You'll see I have a bunch of examples for certain rules, rules 4, So we're going to go over a lot of this stuff with these rules. So the first rule we're going to have is what's called the complement rule. All right. And the definition for it goes like this. For any event E and its complement, All right. And the complement of event we'll call EC. Okay. All right. So let me kind of explain in probability what this means. And I'm going to do a visual for this. Okay. I'm going to use a visual actually with Venn diagrams here. So suppose you have a probability experiment where the outcomes are the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. If event E is equal to the numbers 1, 2, 3, okay, so this is event E, this circle here. What EC represents, the complement represents everything else that could happen. Okay. So if event E is the numbers 1, 2, 3, what's the complement? What are the other results you could get in this probability experiment? Yep. Yeah, that's what the complement represents. Yeah, so the complement is all the other outcomes that could happen. Okay. So for any event E and its complement, if I say, hey, what's the probability that event E happens? One way you can solve it is 1 minus the probability that the opposite of the complement happens. Or you can actually even write this as the probability of the complement happening is 1 minus the probability of the original event. Okay. And you have all used the complement before, and you haven't realized it. Okay. So I'm going to do 2 quick examples of this to kind of show you the complement rule. And the complement rule is actually the easiest rule we have in this class. And what'll happen, and please take note of this, like try to remember this for Thursday. We use the complement rule generally when I ask you to find the probability of event E. And event E is like super complicated when you can very easily find its complement. So if you can find the complement of a super complicated problem, you just do 1 minus it. And that'll make more sense when we get to the later, more complicated stuff on Thursday. All right, let me go. Everybody okay if I go to the next slide and do 2 quick examples of this? Okay. All right, here's the first example. According to NFL.com, I'm going to do a sports example, sorry. Okay. The probability someone was rooting for Tampa Bay to win, which they did, which was awesome. Let's say it was 0.40. Okay. What's the probability someone was not rooting for Tampa Bay to win? Does anybody know the answer? Yeah, right. Look, and you guys are both right. And you got it like super quickly, right? So, how did you do it? And that's the right answer. That's it. And that's just the complement rule right there. So look, we're trying to find the probability was not rooting for them to win. So the probability not rooting to win. Well, that's E. So its complement then is 1. What is the opposite of not rooting them for to win? It's rooting for them to win. 1 minus probability of rooting for them to win. And this is the complement. So this is 1 minus. Well, this, we already know the probability that you were rooting them to win. It's this. And that's the complement rule right there. Okay. No, it's super easy. Like people, you have every single person on the call here. Okay, I know we've had a few people drop off, but every person on the call here has used the complement rule before and just maybe not put a name to it. Okay. All right, so let me just end on this one last problem, okay? For another complement rule, if it's okay for me to go on, if everybody's good. Everybody okay? Okay. So I want to go back to the game of craps, okay? And here's my question. What's the probability you do not roll snake eyes? And I'll explain what that is in a second. Okay, so what is the probability you do not roll snake eyes in the game of craps? I'm just curious. Does anybody on the chat here know what snake eye? That is the right answer. Yes, I'll get there. So Melissa, what is snake eyes? You have it in the chat. Yep, snake eyes is double ones. Brianna's got it too. All right, it's the worst thing you can do. Okay, unless you bet on it happening. All right, so it says, what is the probability you do not roll snake eyes? So here's the thing. I have no idea how to find the probability you do not roll snake eyes. But what I might know is the complement of not rolling snake eyes. Okay. So what is the complement that you do not roll snake eyes? That you do roll snake eyes. Okay. So let's real quickly figure out the probability you do roll snake eyes. All right. Well, how many total outcomes are there for the game of craps again? Yeah. And how many ways in the game of craps can you roll double ones? Yep. So this is just 1 minus 36, 1 out of 36. So you would just change the 1 to 36 out of 36. And that gets you 35 out of 36. And that's the answer. Yeah.
Real quick, I was losing some connection. How did you get the 36 again?
So we're going back to the game of craps. So we did that in here on this slide.
Oh, okay. Thank you.
Yeah, no problem. All right, so here's what I'm going to do. I'm going to save both of these PowerPoints and post them to class. And we're going to pick up here on Thursday. Okay, everybody. And I promise you, Thursday is going to be much, much more interesting class. Okay, I promise you. All right, we're going to get away. We are going to do some coin flip die roll stuff in the beginning. But I promise you, we're going to do so many more interesting problems on Thursday. Okay. All right, I'm going to stop the recording.